Here we have a number of statements and we have to state whether they are always true, sometimes true, or never true. The first statement says that in a parallelogram the opposite sides and opposite angles are equal in measure. Well, this is always true. We saw in an earlier video that the diagonal of a parallelogram cuts the parallelogram into two congruent triangles. We proved that these two triangles are congruent when we were trying to show that the diagonal bisects the area of the parallelogram. So we get two triangles of equal area. So the area of a parallelogram is twice the area of each of these triangles. I was trying to prove that the area of a triangle is half the base by the perpendicular height. So I'd shown before that the area of a parallelogram is base times height, and then the area of the triangle is just half that, half the base times the height. So these two triangles have the same area, but not only that, they're congruent. It's possible for two triangles to have the same area but not be congruent, but they're actually congruent. I'll show you the angles that are the same. These two angles are the same because they're Z angles or alternate angles. This angle here equals this angle here. These green angles are another pair of Z angles. Again, it's because this line is parallel to this line and this line here is parallel to this line for these two equal angles. So two angles are the same in both of these triangles. That means the third angle is automatically the same. So this angle must equal this angle. But these are a pair of opposite angles. So opposite angles of a parallelogram are equal. And it's very clear that these two together equals these two together. So here's another pair of opposite angles. They're equal. Now if two angles and a side are the same in two triangles, then we have the angle side angle condition. See, the green angles are the same, the red angles are the same, and we have one side the same. That's abbreviated ASA. That means that these two triangles are congruent. So it means everything about the triangles is the same. So the side opposite the green angles are the same. So this equals this. So the opposite sides of a parallelogram are equal in length, and the sides opposite the red angles are the same. So this side here equals this side here. A parallelogram which has no right angles has two axes of symmetry. Here is a parallelogram that has no right angles. Let's look at this diagonal here and see if it's an axis of symmetry. Well, we know that this angle equals this angle. They're Z angles or alternate angles. And we know that this angle here equals this angle here. But the green angle is not necessarily equal to this brown angle. These two angles are not necessarily equal. So if we were trying to get the image of, say, this triangle here under axial symmetry in this line here, it won't fit exactly on this second triangle here, unless these two angles are the same. And even if they are the same, we would need sides to be the same. We would need this side here to be equal to this side here. And as you can see, they're not. So the image of this brown triangle under axial symmetry in this line is not this triangle here. So this line is not an axis of symmetry for this parallelogram. Neither is this line here an axis of symmetry, because these two lines have different length. We could of course consider a parallelogram where the sides are all the same, four equal sides. This is not a rectangle, as you can see, because we don't have right angles in it. And we could consider this line, this diagonal, see if it's an axis of symmetry. Well, we know that this angle equals this angle because they're Z angles or alternate angles, and we know that this angle here equals this angle here because we have another pair of Z angles. However, we've got isosceles triangles here. This triangle here is an isosceles triangle, so this angle must equal this angle. Okay, these are the angles opposite the equal sides. So the white angle equals the blue angle. So actually we have 4 equal angles here. These two angles are the same because they're in an isosceles triangle. This angle equals this angle because they're alternate angles. And this angle equals this angle because we have another pair of alternate angles. Or we could say that this one equals this one because these are two angles in an isosceles triangle. These angles are opposite the equal sides. So these 4 angles are actually the same. We also know that opposite angles of a parallelogram are equal to each other, or it's just the remaining angle in each of these 2 isosceles triangles. So actually, for this type of parallelogram, this diagonal is an axis of symmetry. So if we get the image of this triangle under axial symmetry in this line here, this diagonal, we will have this second triangle. Or we could say that the parallelogram is the image of itself under axial symmetry in this line. And we have a similar situation for the other diagonal. We can apply the same reasoning for this other diagonal by considering this triangle and this triangle here. So this parallelogram has 2 axes of symmetry. It has no right angles. So you can see that sometimes this second statement is true. And we know exactly what the condition is. The condition for this second statement to be true is that the 4 sides of the parallelogram must be equal to each other. The diagonals of a parallelogram which is not a square are equal in length. Well, this parallelogram is certainly not a square, and we can see that the diagonals certainly don't look the same. This side here is longer than this side here. We can see that this angle here is longer or larger than this angle here. So if we look at this triangle, we see that this diagonal is of the parallelogram is opposite this angle in this purple triangle. But this angle is smaller than this one here. So if we look at this blue triangle, we see that this second diagonal of the parallelogram is a side of this blue triangle opposite this larger angle. This blue angle is larger than the purple angle. So we can see that the blue diagonal is larger than the purple diagonal. So if we want to call the purple angle capital A and the blue angle capital B, then the side opposite capital A we call small a, and the side opposite capital B in the blue triangle we call small b. And since angle B is greater than angle A, then the sides that are opposite those angles follow this rule also, because you see the other 2 sides of these 2 triangles are the same. See, this side equals this side here, as they're opposite sides of a parallelogram, and well, this side is the same in the purple and the blue triangles. So the sides that enclose angles A and B in both triangles are the same. It's just that B is bigger than A, so the side opposite B, small b, would be bigger than side small a. So we can see that these diagonals are not equal. But are there other situations where the diagonals are equal? Well, here is a parallelogram that is not a square. These 2 sides are not the same, so it's not a square. It's a parallelogram, but it's a rectangle. So the 4 angles are 90 degrees. Let's look at the 2 diagonals. Well, we see that these 2 triangles are actually congruent, but they're also congruent to the 2 triangles formed from the other diagonal. They're congruent to these 2 triangles by side angle side. We can also show this from Pythagoras. If I call this side x and this side y, then the longest side is going to be the square root of x squared plus y squared. But of course, to get the length of the other diagonal, we see we have this right angle triangle here with the same sides x and y. So by Pythagoras, this side is also given by the square root of the sum of the squares of these two short sides. So the two diagonals have the same length, namely the square root of the sum of the squares of the two sides of the rectangle. So we can see that statement 3 is sometimes true. It's true for the case of a parallelogram that is a rectangle. Of course, we don't want this rectangle to be a square, because in this statement we see that the parallelogram must not be a square. So we have to make x and y sides of different length. So statement 3 is true for the case of a rectangle that is not a square. A rectangle is, of course, a parallelogram. Statement 4. The diagonals of a parallelogram divided into 4 triangles of equal area. This is something I proved in an earlier question. This is true. Yeah, this is always true. And I'll just quickly go over that again. We know from a theorem that the diagonals of a parallelogram bisect each other. So the distance from here to here is equal to the distance of here to here. Now let's suppose we want to get the areas of these two triangles. Well, to get the area of this triangle here, we could drop this perpendicular height. Call it h. And I'll call this distance x. This distance from here to here is also x. So the area of this triangle is a half xh. Maybe I should call it b, but it doesn't matter. Let's look at the area of this triangle here. Well, let's take x as its base. So the bases of both triangles have the same length. But the height is got by dropping this perpendicular. We'd have to extend this base here to show the height of this triangle. But anyway, the area is half xh. So the areas are the same. These two triangles. Now what about these two here? Well, we've shown that this triangle is actually congruent to this triangle here. So the area of this triangle is equal to the area of this triangle, because the two triangles are congruent. Now, it's important to realize that these two triangles are congruent, but these two are not necessarily congruent. These two have the same area, because all three of them have the area half xh, but these two are not necessarily congruent. But these two are definitely congruent. These two are always congruent. The reason why is because we have two sides the same. This side also equals this side, because the diagonals of a parallelogram bisect each other, and the angle enclosed by the equal sides are the same, because these are opposite angles. So by side angle side, we have that this triangle here marked in red is congruent to this triangle down here. These two triangles marked in red are congruent. But we can't say the same for these two. We can't say that these are congruent. But at least we know they have the same area. Because if these two have the same area and these two have the same area, then obviously these two are equal in area to each other. Now, in a similar way, we can show that this triangle is congruent to this triangle by side angle side again, but this time we're talking about this pair of opposite angles. So the 4 triangles have the same area. Not because the 4 of them are congruent, they aren't. It's just that the red ones are congruent and the blue ones are congruent. But the red and blue triangles have the same area, but not necessarily congruent. Statement 5. All the sides in a right-angled triangle are of different lengths. Now, the largest angle in a right-angled triangle is the right angle. The other two angles have to be less than 90 degrees, because these two angles have to sum to 90, because 90 plus 90 is 180. So if these two angles have to sum to 90 degrees, they must both be less than 90 degrees. Okay, so the largest angle is the right angle. What about the longest side? Well, the longest side in any triangle is opposite the largest angle. So we've established that this side here is longer than the other two sides. So its length is obviously different from the other two sides. But of course the other two sides could have the same length. I could have an isosceles right angled triangle. I can make the two short sides the same. I obviously can't make one of the short sides equal to the longest side. but at least I can make these two sides equal to each other. So this statement is not always true, because we can't say that all the sides in this triangle are of different lengths. Two of them have the same length. But of course it is sometimes true. I could have made this triangle have the two short sides with different lengths. That's very easy to do. Maybe it's not so clear in this picture, but here's maybe a better picture. Now it's clear that the three sides have different lengths. So this type of triangle is called a scalene triangle. Whereas this one, as we know, is called an isosceles triangle. Now we can't draw an equilateral right angle triangle. The three sides will be the same, but in an equilateral triangle, see, in an equilateral triangle the three angles are also the same and they're equal to 60 degrees. So we can't have a right angled equilateral triangle. So statement 5 is sometimes true, namely when we have a scalene right angled triangle.